When working with differential equations, it's often helpful to go back and ask, how do similar processes work with algebraic or non-differential equations, or for most of us what we'd call just regular equations? There's two important differences in the processes we use. One is solving, and we're going to see that that's actually quite challenging for differential equations, as it would be for solving complicated regular equations. However, there's another part of the process which is verifying a solution, and that's usually very straightforward. So it's important to recognize that while solving can be hard, verifying is either easy or straightforward, depending on what word you want to use. And it's going to behoove us to try to verify solutions wherever possible, especially if we're going to spend a lot of time solving an equation, just to make sure we have the right answer. So, to highlight how that process would work, let's look at this problem here. Determine which of the two functions, y1 equals k e to the t, or y2 equals e to the kt, with a k in the exponent, which of those is a solution to the differential equation below. Now we've seen this equation before, so hopefully one of those two solutions looks familiar, but the key thing for right now is to understand that we can verify a proposed solution by subbing it into the equation and seeing if it actually does satisfy the equality that's implied there. So here we have two proposed solutions. Let's try each one individually and try to sub it into the equation. So sub the proposed solution into the equation. And then what do we look for? Well, we look for, or we check or verify, that the resulting left-hand side equals the original right-hand side when we do that substitution. So let's call this 1 here. If we use 1, then we already know what y is. It's going to be k e to the t, but what we don't know is dy dt. We need the left-hand side, that's dy dt, and that's the derivative of our proposed y value, which is k e to the t. And that is easy to evaluate. So again, the verification step here is straightforward as a process. We simply differentiate and we get k e to the t again, and that would be the left-hand side of our equation. The right-hand side of our equation is the differential equation here, is ky, and we have to be careful. We have to use the same y value we did before. So k times y1 is k e to the t, and then we realize, wait a minute, we have a k squared e to the t. So what we've said is that the left-hand side of the equation would equal k e to the t with the solution, but the right-hand side of the equation, if we expand it out completely, would be k squared e to the t. These are not equal, and so that immediately means that y1, this guess that k e to the t is a solution, is actually not a solution, because when we plug it in, it doesn't satisfy the equation. Then hopefully remember, oh right, when we had this form before, the k snuck into the exponent, that seemed to work. And so we can verify that here with equation 2, or rather solution 2. We go through the exact same process. We look at the left-hand side, and that's the derivative of what we think y is, but this time we think y is e to the kt. That's our proposed solution. And we know that we differentiate e to the kt with the chain rule. We're going to have a k multiplier out front. Meanwhile, the right-hand side is k times y. So this is always going back to the differential equation, subbing in our proposed y value. So our ky in this case is k times our y, which is e to the kt. And now we see that the left-hand side, k e to the kt. Right-hand side, k e to the kt. These are equal. And that means that y2, e to the kt, is a solution to the differential equation. So that's the compare and contrast. Again, someone's provided us the solutions, and we're simply verifying whether or not they're actually real solutions to the equations. Here's a more complex example for a more complex differential equation, and we'll see how this works out. So someone has proposed to us that g of x, sine minus cos x, is a solution to this differential equation and also satisfying the initial conditions here. What we have in this case is 3 equations that have to be satisfied, and quite frankly, this looks like the most complicated. If a solution satisfies all 3, it'll have to satisfy these 2 first. So let's try the easy equations first and just make sure that the solution does or does not satisfy the initial values first. In this case, y of 0, this is going to be what we're going to call our y. It's our proposed solution. At 0, we should get a value of -1. Well, we get that with our left-hand side being sine of 0 minus cos of 0, and cos of 0 is 1, and we have a negative up front. That is -1. That's equal to the right-hand side, so we get a check mark for that for equation 2. I'll label all the rest of them here. For equation 3, which should also be fairly straightforward to check, we need to pre-calculate the derivative. We're going to need y prime. Well, that'll be the same as g prime, and that'll be the derivative of sine is cos. The derivative of cos is negative sine, but there already is a negative, so that'll be positive sine. And then we can sub in our values for the left-hand side of equation 3. That's y prime at 0. That'll be cos of 0 plus sine of 0. Cos of 0 is 1, sine of 0 is 0. And we get a value of 1 out of that, and yes, indeed, that equals the right-hand side of equation 3. And so we get a check mark for that. Now, the most complicated one is the first equation, the actual differential equation, and for that, we need y double prime, or the second derivative here. Now, we've already calculated the first derivative, so that's handy. So what we're going to do is take another derivative and get to the second derivative. The derivative of cos is negative sine, and the derivative of sine is positive cos. Now we can sub in to the left-hand side of equation 1, the second derivative, negative sine of x plus cos of x. That's our d squared y dx squared, second derivative, plus the other part of the left-hand side is y, and we've been told, or as a proposal we've been given, that y is equal to sine of x minus cos of x. And that's the left-hand side in its entirety, second derivative plus y. And we see pretty quickly that we have a negative sign and a positive sign. Those cancel out. We have a cos of x and a negative cos of x. Those cancel out. And so we end up with the left-hand side equaling 0. Well, that's exactly what the differential equation should equal, because that's what is on the right-hand side of the equation. And so we've also satisfied the third equation given to us, the most important one as well, the differential equation itself. We can conclude that sine of x minus cos of x is a solution to this initial value problem, IVP. If it had failed any one of those 3 equations, then we would not have a solution. So what we're going to be doing as we move forward is getting solutions ourselves, constructing them ourselves, and as a last step, when it seems feasible and helpful, we'll be verifying our solutions as well.